Okay, so in this last neutrino lecture, we are going to look at two aspects. So I've essentially divided the lecture in two. We will look at neutrinos in the problem of electronic mixing. So we look where the flavor structure that I observe in the electronic sector could come from. And then I'm going to talk about neutrinos in cosmology. I've picked out three kind of key topics. The area is very broad, but I think we can cover this in the time allocated. So I will not be here for the Q&A session on Friday. So if you have questions, I will leave some time at the end so that you can ask them today. So let's start by a recap of where we are with the neutrino. Now I will focus on the flavor structure. So I will focus mainly on mixing angles and the CP violating phases. So I showed you this morning. So we know the three angles, theta 2,3, theta 1,2, and theta 1,3. So notice the values. I mean, they are interesting, especially because theta 2,3 is maximal or very close to being maximal. The next generation of experiments is going to pin down this value much better. Theta 2,3 is large, non-maximal, but definitely a large value. And the theta 1,3, well, is relatively largish, but not too far from zero that we cannot come up with a flavor model to explain this. What is important is the mixing is very different from the quark sector. And so somehow this offers a different insight on the flavor problem compared to what is suggested by the quark sector. How about CP violation? This is in the lepton sector. This is really a key issue. There are some hints, and where do they come from? So this is the allowed ranges of delta and sine squared theta 1,3 when you fit the data. So these lines here correspond to long baseline experiments, in particular T2K. And these, instead, these kind of straight bands are the results from reactor neutrino experiments. They have no sensitivity to CP violation because, remember, the probabilities are disappearance probabilities of anti-nu-E's into anti-nu-E's in the two oscillation approximation. There's no sensitivity to CP violation, so they are independent from delta. So when I put these two together, these are the results in 2014, and now these regions have shrinked much more, and also these bands here. So what you get is the plot here in 2016, you get some indication that probably the delta phase, or at least the delta phase likes to be around 3 pi over 2. Is early days. We don't know if these results will be confirmed. We need much more information. But this kind of is the picture. I mean, these results have consistently moved in this direction. So, you know, each new set of results tend to shrink a little bit this region. So there's some, I mean, the data seems suggestive that this indeed is the picture. If this is the case, then we have maximal leptonic CP violation in due to a delta phase, which is around 3 pi over 2. No clue about the Majorana phases, because the Majorana phases enter only neutrino-less double beta decay, so we have not observed it yet, so we have no information whatsoever on them. So why CP is, yes? Sorry? This is for normal ordering. This is what you are asking. So this is for normal ordering. For inverted ordering, so the data seem to prefer normal ordering, which means that if I try to fit the data with inverted ordering, I mean, still there's not enough information to distinguish the two orderings. There's a slight preference. But what happens is that kind of this region shrink because the data prefer normal ordering. So somehow the there is less space if you want to accommodate a delta phase for inverted ordering. But again, also in that case, the data tends towards large CP violation. So, yes.
This in leptonic sector?
Yes, so that's my, let's see, this slide. So you look at the difference in oscillation probability for neutrinos and antineutrinos. If you remember, for neutrinos is the U matrix which matters. For antineutrinos is a U star. So if you have CP violation, then you'll go from U to U star. And when you do that, and actually you compute this, this is called a CP asymmetry, you find this dependence, the dependence on all the three angles, which is to be expected because this is a genuine three neutrino mixing effect. If you had a two neutrino mixing, you have no Dirac phase in the game. So you expect to have all the three angles involved, and indeed is the case. The phase enters here, and then the mass square differences, because again, being a three neutrino effect, if I set one of the mass square differences to 0, in that case, I cannot see CP violation because I go into the two neutrino oscillation approximation, and there, again, I have no CP phase appearing. So we can skip the previous slide. You can look it up on the online. So if I now I do this, I look at the oscillation probability, nu mu into nu e, and I need to look at the three neutrino oscillation probability, and typically there will be the presence of matter effects. This is the expression I get. I already showed that yesterday to discuss matter effects, which are embedded in this RA parameter. This time we're interested instead of the term which depends on delta. This is where the difficulty comes about. So if you look, the dominant term is this one here, which doesn't contain delta. This is so-called atmospheric term, and it's controlled by theta 1,3 squared. Now, if theta 1,3 were a factor of 10 smaller, this would not be the dominant term. They would be roughly of the same order. Because theta 1,3 is quite largish, then it means that this probability is sizable and can be observed in experiments. Indeed, we have already done that. But it means also that CP violating effects, which are suppressed by delta m squared 2,1 over delta m squared 3,1, are subdominant compared to the dominant atmospheric term oscillations. And therefore, now it becomes, you need great precision in measuring this probability because you have to disentangle a few percent effect over a probability. There's this dependence on the energy. So as I go to lower energies, this term increases in importance. So this also tells that if you want to see CP violating effects in neutrino oscillations, if you can go to lower energies, you will enhance the CP violating effects, and it will be easier to measure them. There is obviously a difficulty. Typically, fluxes of neutrinos at low energies are suppressed, and the cross-section, detection cross-section also are suppressed at low energies. So you enhance the effect, but you reduce the number of events you see because of the experimental conditions, cross-sections, fluxes, etc. And so it is a very complicated problem where you try to maximize the sensitivity, and this is what large experimental collaborations have done and are doing. And you already have some sensitivity from T2K, NOVA, etc. Now, this generation of experiments will actually be able to tell us much more, collecting more data. This is a kind of relatively a couple of years old plot of sensitivities of what T2K could do with and without adding NOVA. Combining different experiments helps in disentangling the CP effects, CP violating effects, which come from matter effects from the intrinsic ones. And so you gain a lot. You see, if I add, for example, T2K and NOVA together, what we are expecting is the next generation of experiments, Dune and Hyper-K, these, and T2HK. These are the experiments which are basically designed to hunt for leptonic CP violation. And if it is confirmed that the value of delta is around 270 degrees, 3 pi over 2, then they will be able to get over 5 sigma, which means a discovery of leptonic CP violation in not too many years. So now, how to explain the flavor structure we observe, so the mixing angles we see, and if we find it, leptonic CP violation. So this is a very complex problem from a theoretical perspective as well. And it comes, ultimately, the flavor structure is given by the structure of the mass matrix you start from. So if I Imagine that I have a model, which a flavor model, for example, or another model, which gives me a certain mass matrix for the neutrinos. I have to diagonalize it. We have done that in the previous lecture. I will do that by using one unitary matrix. I will find the values of the masses. These indeed are the values of masses. These are the eigenvalues of MM, which are the masses of the neutrinos. And then this is the matrix. Then I consider the massive states. This will be equal to U dagger, new left. These are the flavor states. These are the massive states. So this enters the charge current Lagrangian. So if I can find a specific structure for Mn, maybe I can explain the specific mixing angles that I find in the charge current Lagrangian. An example, a very simple example, imagine a matrix 2 by 2, which is of this kind, A, B, B, C. We know that it is symmetric. So so we know what is the angle which diagonalizes this. This is twice B divided by A minus C. So, for instance, if I have a model which tells me that A is very close to C, then I get maximal mixing. And then I can find the eigenvalues, and again, depending on the ordering, whatever I find experimentally, I can constrain the parameters A, B, and C. So, sorry? Oh, the difference of the diagonal terms. Right? These are just parameters. I want to show you that if I have a specific form, so let's say I have a model which tells me that this is A. So, for example, a mu-tau symmetry, a symmetry which tells me that these terms are equal to these terms. And in that case, immediately, I get pi over 4. So if I have a reason to have a specific values of the entries of the mass matrix, then I have a reason why I end up with special values of the mixing matrix. And that's why 45 degrees for me is suggestive of some symmetry in the flavor sector. Now, you remember yesterday when we discussed mixing, do the charge leptons mix or not? And there was some consensus that they don't mix. In reality, it's the way I pose the question. Because in asking the question in that way, I essentially choose a specific basis. I choose to define the flavor basis as the basis in which the charged leptons are massive. This is a very, in my opinion, good choice of the basis, because this is what experiments do when you you produce a charged lepton in an experiment, either by measuring energy momentum or even the environment itself, selects one of the masses. The masses of the charged leptons are quite different, so it's very difficult to produce a coherent superposition of charged leptons. You will select one of them, and you call that the flavor. So experimentally, this is an excellent choice, but from a theoretical perspective, you can make other choices of a flavor basis. For instance, I could say a basis in which this or something similar in the charged lepton sector happens, so in which the charged lepton mass matrix has a specific structure. I can define that as my charged lepton flavor basis. And so I will have, okay. Why don't we do it on the slides instead of spending a huge amount of time writing all the terms? So you will have the charged lepton Dirac masses that where I have two unitary matrices needed to diagonalize it, and I will have the mass matrix for the neutrino symmetric, where I need just one mass matrix. So now, this is what I define as my flavor basis. So when I have to diagonalize this mass matrix, and so what are the massive charged leptons, that is what I observe, there will be a matrix here which relates the flavor basis, my choice of flavor basis, with the massive basis of the charged leptons. In the same way for the neutrinos, what I need to diagonalize, and so there is this mixing between the neutrino flavors and the neutrino massive states. Both of them enter in the charge current interaction because this is what are my charged leptons with definite mass, but I will have this matrix which relates the massive charged leptons to what I chose as a flavor basis because it works nicely in the flavor model I'm considering. And similarly, I will have this. So the mixing matrix that I observe in an experiment is the product of the mixing matrix that comes from the diagonalization of the charged lepton mass matrix and on the left side, and the matrix which diagonalizes the neutrino masses. So in some sense, the physical observable is the product of the two. So asking if the charged lepton mix or not is, if you want, a not very well posed question, because what I can only observe is the misalignment between the charged lepton mass states and the neutrino mass states. And this is the PMNS matrix that I can try to measure. In fact, in many models, you will have special structures. I will show you an example of these two matrices, and it is the product of the two which ends up giving you 45 degrees and 9 degrees and 33 degrees, etc. So what are the ways to give a special structure to this mass matrix, to these two mass matrices? There are many ways. People have tried to relate this to the quark sector, having ansatz, putting zeros, choosing a base in which you have zeros in some of the entries, then you diagonalize it, and then you try to get the PMNS matrix. What I consider is the most studied approach is with symmetry. As I said, 45 degrees is a bit suggestive as a number. So people have devoted a lot of attention in trying to come up with flavor symmetries. So the idea is that the three flavor charged leptons and the three neutrinos live in representations of a group, a flavor group. And then you write down the Lagrangian, you break the symmetry. This will give you specific entries in the mass matrix, which you diagonalize, and you will obtain the PMNS matrix. I'm going to show you one explicit example of that. There's a bit more information in the slides as well. So if we're looking at this symmetry approach, so first of all, you choose a symmetry, which could be global, like SU3, SO3, but a lot of study has gone recently in discrete symmetries, symmetries which have a discrete number of elements. The simplest one is Z2, has only 2 elements, +1 and -1. But people look at slightly more complicated things like A4, S4, S3, and then much more complex groups. So the thing you do, you put the neutrinos and the charged leptons into representations of this group, and then you have to write down the Lagrangian. This will give you a matrix which typically is not the one which is compatible with data. Typically will give you a θ13 which is 0 or a θ23 which is exactly 45. You need to introduce corrections to get to the values you observe experimentally. And there are various ways. So you add perturbations. Which come from, from the charged lepton sector, from breaking the symmetry explicitly or other ways. The fact that θ23 is relatively large has posed serious challenges to this approach, because getting 0 is very simple. Getting 80 degrees is less obvious how to do that in a kind of symmetry approach. And so what kind of basic structures of the mixing matrix have been considered? Let me mention just the tri-bimaximal mixing, because this has been very much studied in the literature. So this is a matrix which is of the kind square root of 2 over square root of 3, 1 over square root of 3, 0. So you see already where the problem is. Minus 1 of the square root of 6, 1 over square root of 3, 1 over square root of 2, 1 over square root of 6, minus 1 over square root of 3, and 1 over square root of 2. So immediately you see that the problem lies in generating a relatively large value for an angle without spoiling the idea of the symmetry, because if you start adding corrections which are too large, then why do you start using the symmetry in the first place? You should change symmetry or adopt a different approach. So let me give you two examples. One is the mu tau symmetry, because this generates exactly this maximal mixing for theta to 3, which is nice experimentally. So the first example is the mu tau symmetry. And in this case, you will have exactly the matrix I was discussing before. Because of the mu tau symmetry, these two terms are equal. And so you immediately get an angle in the 2-3 sector, which is pi over 4. You have to do it in 3 generations, so you will have a more complex matrix, and so in this way you can generate also a value of theta to 1, 3, etc. But you need to introduce also corrections, because you typically end up with a value of theta 1, 3, which is too small. Some nice features is that you can connect the values of the masses to the values of the mixing angle, so it's quite constraining as a model. The other example I want to talk about is an example of a discrete symmetry, and I will use A4 because this is one of the most studied cases in the literature. So this is the group of even permutations of 4 elements, and we go. And it has 12 elements, which are given here, which can all be expressed in terms of a part of the identity, T and S, so you can construct the full group in this way. And it has representations which are identified by 1, 1 star, 1 prime, 1 second, and a 3. It's nice to have representations which are 3, because then you can put there 3 generations of leptons. And so you have to make your choice for how to distribute your fermions, charged leptons and neutrinos, to the representations of the field. This is the same as you do for a gauge group, for instance. But there's clearly these have no associated gauge bosons to them. So you'll put the leptonic doublet into the 3, and the 3 charged leptons into the 1, 1 prime, and 1 second. Now, how can I write down the terms in the Lagrange? And I have to know what are the byproducts of 2 fermions. So, for example, if I have a 1 prime and 1 prime, I will get a 1 second, and so on and so forth. So then I will have to add a scalar that, when breaks down, then gives me a mass term that I want. So, for instance, if I have a 1 second, I will need a 1 prime, so I will add a scalar which is a 1 prime, so that I have the fermion, which is some fermion, let's say 1 prime is a mu right, so I will have mu right, and then I want, what do I want? Well, here. So I will have my, for instance, mu right, phi L, and then this is a non-renormalizable term. I will have an HDD over lambda, because I need to make SU2 conserving. So once the phi and the HD give a mass term, then get a VEV, then this will give a mass term to the muons, and so on and so forth. I have all the other terms. Then I have these LL UU terms. These instead will give us the terms for the neutrinos. And so by doing this, assuming that the flavons get these specific values, these are called the flavon VEV alignment problem, you will get these mass matrices. Then I diagonalize the charged lepton mass matrix and the neutrino mass matrix. I make the product of the 2 mixing matrices, and I get exactly that try by maximal mixing matrix, then I add some perturbations, and I get theta 1, 3 equal to 8 degrees. So this is the basic picture, and you can do the same thing with using many other different groups, etc. Where, I mean, the construction is quite beautiful because I'm using a symmetry in the flavor sector. Part of the problem relies in how I break the symmetry and how I generate the masses. So why do I have these choices of the webs for the flavons is very difficult to explain. So, well, there's been various attempts, but in my opinion, this is where you have kind of the difficulty of these type of models in explaining why you have these special values of the flavons. If you didn't have these specific choices, you wouldn't end up with such nice matrices for the charged leptons and neutrinos that you would not get to try by maximal mixing or any other mixing you want in your model. Yes, yes. But you need that, but then you also need then a reason why the choice of your couplings in your potential. So, I mean, you can translate the problem, you know, there's been also other ways in which they have justified these values using extra dimensions, etc. So it is true, you can justify it, but again, but it remains a kind of a difficulty to be kind of solved in the problem you are looking at. It's not the only approach. Other people have used the symmetries, but instead of kind of having these constructions instead of webs, etc., they have looked at a more geometric structure of the groups. And in that case, they can justify at least some of the parameters in that way. It's relatively recent work in the continuous groups in SU3. So this is just to give you a little bit of a flavor of how you can try to explain the mixings you observe in the leptonic sector. So I want also to make a suggestion, which is I prefer to talk about leptonic mixing instead of neutrino mixing, exactly for the reason I gave you earlier, that what you observe in the charge current interaction is the product of what comes from the charged lepton sector and the neutrino sector, and unless you make a choice of bases, as we did yesterday at the beginning of the lecture, in reality, you have the product of the two, so it's better to talk about leptonic mixing instead of neutrino mixing. So how are you going to try to disentangle? I mean, in the literature, there are hundreds and hundreds of papers on these flavor models. How are you going to try to kind of experimentally test and at least exclude some of them? But the only thing you can do is to measure precisely the oscillation parameters. And so there are two main kind of things to determine. One is the mass ordering. This is not so important for discrete flavor models because there you explain only the mixings and not the masses. But for other models like mu tau, symmetry, etc., this is a key piece of information. And the other thing is the values of the parameters. For example, this was done several years ago now. This was a compilation of the various symmetries that were studied in the literature with the hierarchy, now I call it ordering, that they were predicting, the values of the angles. In particular, a lot of emphasis was put on the predictions for theta 1, 3. So having measured theta 1, 3, already you can get rid of all the models which are not kind of in greenish. So a lot of kind of models have been discarded now, but of course new ones have come up that now all satisfy the value of the theta 1, 3 you observe, but they have other predictions. Typically, they have predictions on correlations between the oscillation parameters. These are called sum rules. For example, these are the atmospheric sum rules where you relate the deviation from 45 degrees of theta 2, 3 to theta 1,3 and the value of the delta phase. This arises in many of the flavor symmetry models which are considered. And another sum rule which again arises in many of these models, especially the ones where the corrections come from the charged lepton sector, are called solar sum rules. And again, I can express the delta phase in terms of the other oscillation parameters. So if you measure precisely theta 2,3, theta 1,3, and delta, you can exclude many of the models, and similarly in this case here. And this is an example. For instance, this is one of the sum rules, the atmospheric sum rule that I showed earlier, which corresponds to this line here. And this is the current situation of delta versus sine squared theta 2,3. So you see it's okay with the normal ordering, but already if I go to the inverted ordering, this sum rule is in tension with the data, and so which means that this model is somewhat disfavored by the data. And in the future, we will be able to do much, much better than this. So, okay, good, because I want to leave some time for the end. As I said, the literature is very, very broad. If any of you is interested more in this, I can suggest some reviews. In particular, there's a physics report by King and Loon, which is very comprehensive in discussing discrete flavor symmetries. But I want to just give you a little bit of a taste on how you can approach this problem and what insight into the physics this can give you. So now let's change completely topic and move on to neutrinos in cosmology. This is also kind of very relevant because neutrinos are the most abundant known fermions that are there, are the oldest relics which are known. I mean, there's also dark matter, but we have not observed that yet. We know that relic neutrinos come, at least in the standard cosmological picture, from their decoupling at the MeV. So in some sense, we can trace back the evolution of the universe up to Big Bang nucleosynthesis via looking at the impact that neutrinos have had since then. So I've selected 3 topics in this area. One is kind of just looking at standard neutrinos in the early universe, how they decouple and their contribution to hot dark matter, because this is the way that I already mentioned on how probably in the future we will be able to put the best bounds on neutrino masses or even detect them with the caveats that I was saying before about systematic errors and the underlying cosmological model. I want to mention sterile neutrinos as warm dark matter because these, together with gravitinos, are the most studied candidates for warm dark matter, which is somewhat intermediate between hot and cold dark matter. And I want to mention a little bit more in detail leptogenesis that Yossi has already mentioned earlier. I want to discuss exactly how this come apart and some ways in which you can get some information about leptogenesis. It's not possible to test it because it happens very high scales, but at least we could try to understand how likely is as an explanation for the baryon asymmetry of the universe. So first of all, we need some useful formulas, because now we deal with the early universe, so we deal with thermal plasma. So neutrinos will have a Fermi-Dirac distribution to which I can associate a temperature, a number density, and an energy density. So let me first recap for you. Some useful formulas. So as I said, they will have a Fermi-Dirac distribution, which is given by 1 over the exponential of P minus, if they have a chemical potential, mu nu divided by T, plus or minus 1. In this case, it's plus 1. This is in general both for Dirac, Fermi-Dirac and Bose-Einstein. In the case of the neutrinos, the equilibrium distribution will be proportional to the number of degrees of freedom and the temperature to the cube, with some factors which come in from their distribution of 4/3. Then remember also that the entropy is equal to 2 pi squared divided by 45 G star, and again at e to the cube. So the number density for a relativistic particle is proportional, scales with the temperature as the entropy scales with the temperature. Now, in the notes you will find also the non-relativistic case, but it's less relevant for us for neutrinos. So, and then when do neutrinos decouple? So what is the picture in the early universe? So neutrinos are in thermal equilibrium with the plasma. So in the plasma you will have electrons, positrons, photons, and depending on the energy, if you go to sufficiently high energies, muons and taus and quarks, etc., etc. So let's go to temperatures around the MeV. So you will have only E plus, E minuses, and photons. And neutrinos, for example, you will have all the interactions like E plus, E minus going into neutrino, antineutrino, and vice versa. Similarly for, you have charge current interactions, etc. So all weak interactions will be in equilibrium. And so these will go both ways. And so there will be a constant production and annihilation of neutrinos, which keep them into the Fermi-Dirac distribution. At some point, remember that the universe is expanding. So at some point, these interactions become too slow to keep up with the expansion of the universe. It's like that the probability of two neutrinos encountering themselves and going to plus E minus or vice versa becomes essentially zero. These interactions don't happen anymore. How can I quantify that? What I do, I look at the interaction rate. And this is essentially given by the cross-section multiplied by the number density. And I compare that with the expansion rate. When gamma becomes smaller than h, then the interaction rate is too slow, and these neutrinos, these interactions stop. The neutrinos decouple from the rest of the plasma. And the only thing they will do at that point is to redshift their momentum till they become non-relativistic if they have a mass in the sub-eV region. So now let's look at the temperature then. So we have to compute the time, the temperature at which this equality lies. You can do it kind of more precisely, solving the Boltzmann equation and seeing that this is indeed the time in which kind of you have the decoupling of the particles. So we need the cross-section and the number density, and we need the interaction rate. So let's start with the cross-section. These are weak interactions, so you can just, on kind of dimensional grounds, this will be given by a GF squared and a T squared. So in general, you can make a lot of these order of magnitude estimates for the early universe before going to a full detailed computation. Usually they are good enough to give you a feeling of what are the scales, the temperatures involved. Weak interactions, so I will have a GF squared, and I have to compensate to get the right units of mass, of energy, to get to the cross-section. That's why I'm adding a T squared. I guess that's clear. The number density, that we said scales as T cube because we are dealing with relativistic particles. And then in the radiation-dominated era, H goes as T cube over M Planck. In the notes, you will have all the right factors included. So now let's do this. So I have a GF squared T to the fifth, which need to be of the same order of T squared divided by M Planck, and this will give you a temperature of around 1 MeV. If I do it more precisely, I will see that muons and taus, which don't have charge current interactions, decouple slightly earlier than electron neutrinos, but more or less they are all at the same time of 1 MeV. This is a very interesting time because it's just before Big Bang nucleosynthesis. And so neutrinos at this point constitute kind of a very sizable, carry a lot of energy in the early universe. And so if I start modifying, for example, the number of neutrinos, I can modify the subsequent processes. For instance, I modified Big Bang nucleosynthesis. So that's a way by constraining, that's a way of constraining the number of the relativistic degrees of freedom that you have, in particular the number of sterile neutrinos you have, if they are fully thermalized at the time. So what happens since, remember that just after this 1 MeV, the E plus E minuses also start annihilating and dump their energy into the photons, reheating them a little bit. Instead, the neutrinos don't partake of this reheating because they are decoupled. So the temperature of the neutrinos is slightly cooler than the temperature of the photons by a factor of 4/11 to the 1/3. So it's not a very large factor, it's just slightly colder neutrinos. And for the rest, as I said, they redshift, becoming at some point non-relativistic when the temperature drops below, or their energy, because their energy drops below their mass. So right now we can expect at least 2 neutrinos to be non-relativistic. We don't know the third one because the third one could have a very, very small mass, so could still be relativistic, or could have a mass which is sizable. So the third one we actually do not know. Now, they contribute also to the energy density of the universe, because especially, so if they are non-relativistic, then if I will get, let me put the h squared here. This is the energy density in neutrinos divided by the critical density. And the energy density, they are non-relativistic, so will be the number density multiplied by their mass divided by rho critical h squared. And I will get that this is the mass of the neutrino divided by 91.5 EV, well, roughly 100 EV. So if I, for instance, have a 1 EV neutrino, I know that this will give me an omega h squared roughly of 1%. And this is because of this contribution, then I can deduce constraints on the mass of the neutrinos, in particular the sum of the masses, because the universe, at least in large-scale structure formation, doesn't feel the flavor of the neutrinos. So, well, let's look at it more in general. So when are the neutrinos impacting in the universe? Let's forget for the time being leptogenesis, we'll talk about that later. So you have neutrino decoupling at around 1 second. Immediately after you have Big Bang nucleosynthesis, and here but the flavor of neutrino matters because it can impact on the weak interactions which are at play in Big Bang nucleosynthesis. But the most important constraints come from the number of relativistic degrees of freedom you have, I already mentioned. And then much later on, there is large-scale structure formation. So how does that work? Well, I'll come to that. This is just controlled by gravity, essentially. So what matters is the sum of the neutrino masses. You cannot access individually each neutrino because gravity doesn't kind of distinguish the flavors. And then right now you have these relic neutrinos, which are quite a large number, roughly 100 per centimeter cube. So is a sizable amount. And the question is that we discussed already yesterday, can we observe them? Because this would be extremely interesting. So, okay. Neutrinos, so far, the only known component of dark matter, they constitute a hot component because they are, they decoupled relativistically, and then they remain with a very sizable velocity for a very long time. And so they tend to erase structure. So what is the basic picture? So the idea is, so how do large-scale structure work? So essentially, you start with a density of dark matter which is non-uniform, has all these kind of overdensities and underdensities, and then where you have an overdensity, the gravitational potential will be deeper, the surrounding matter will tend to fall into this potential well, making this overdensity grow even further, and following this process, you end up creating the structures we observe, so galaxies, clusters of galaxies, etc. Now, if part of this dark matter is hot, so if part of this dark matter is in neutrinos, neutrinos free stream, they are too fast. They are either relativistic or nearly relativistic. And so what they will do, they will be able to escape from these regions, but not over infinite distances. There is a time scale associated to these processes. So they will be able to travel a certain typical distance. So for scales bigger than this typical distance, they will behave as cold dark matter because they have not been able to travel farther, so they will stay within this scale. And so there, the structures will more or less develop as for cold dark matter. But instead, what they will do in here, they will smooth out a little bit the overdensities and underdensities. So they will tend to erase the amount of structures at smaller scales. And this is exactly what you see if you're looking at what quantifies the structure. Let me see if I have a slide. That quantifies these the distribution of densities, which is the power spectrum. So if I look at the power spectrum of neutrinos, in presence of neutrinos compared to lambda CDM, what I find is this is called the transfer function. So you will see that at a typical scale, the presence of neutrinos, this is for larger and larger masses, will erase the structures that you observe. So, but then conversely, if I measure the power spectrum, as I can do with in various ways, mainly looking at the tracers of the dark matter densities, which are galaxies and things of that kind, or looking at lensing, I can reconstruct the power spectrum and I can compare with the predictions, and I can put a bound on the masses. The larger the masses, the more kind of suppression I have of the neutrino, of the power spectrum. And this is the way in which cosmology is currently putting what are the strongest bounds on the neutrino masses we have, down to the level, as we were discussing at some point earlier, of the sum of neutrino masses smaller than around, let's say, 0.3 eV, with some caveats. And the plans are to be more and more sensitive, in particular using lensing and testing the underlying cosmological model, to get down to a sum of masses of 0.05 eV. 0.05 eV is the minimal contribution you can possibly have. Remember, the sum of the masses, if you have normal ordering, will be at least, so you have M1, M2, and M3, where M1, I neglect, this is roughly 0.01 EV and 0.05 EV. So at the very least, you need to have something which is around 0.06 EV. In the inverted ordering, instead, these two masses are roughly of the same order, you will get 0.1 EV. So there are claims that say that with cosmology, we will be able to reach a precision such to distinguish these two cases, even using cosmological data. Okay, so this is about kind of the standard neutrinos in cosmology. What I want to mention next is, we discussed this already yesterday, sterile neutrinos as warm dark matter. So sterile neutrinos are, as I already mentioned, neutrinos which don't carry any SU2 or other standard model charges, so they don't interact with the standard model, but they can mix with the other neutrinos. I remember that I wrote earlier on that 4x4 mixing matrix. So what I'm talking about is not really the sterile neutrino, I'm talking about the N4, the massive neutrino, which fills a little bit the standard model interactions via its mixing to the active neutrinos. So this N4 will be mainly in the sterile neutrino direction, so this is roughly 1, but it will have a small component of active neutrinos as well. So, and via this, it can be produced in the early universe via oscillation. So what happens? Think back, so this is sterile neutrino as warm dark matter. So till you have neutrinos in thermal equilibrium, so above 1 MeV, you have interactions, for instance, of this kind. And here you have nu and nu bar. Now, with a probability which is controlled by U A4 squared, you will be able to produce here a nu 4. And in this way, you can populate the nu 4 distribution and generate a sizable amount of them. Now, because the interactions are always suppressed by UE4 squared, you expect that they were never in thermal equilibrium, at least at relatively low times. So you can produce them, but then they remain decoupled. They don't do anything else. They don't interact back. They just contribute to the dark matter of the universe. So this is the picture. So they decay as well. Sorry. Let me say it right away. So this is the basic production mechanism. Then they decay. Essentially, you can see it how. So you have nu 4. You pick up the active component, and this can decay via a Z into 3 neutrinos. So this is controlled by the mixing angle and the mass of this particle. So the decay rate goes as the mixing angle. You will have a GF squared and the mass to the 5th power. So if I am at sufficiently low masses in the KV region and sufficiently small mixing angles, then it doesn't decay enough over the time scale of the universe. It's a stable particle, and so it can constitute the dark matter. What this also is interesting because this instead gives rise to the possibility to detect, because it can also decay into neutrino photon with a branching ratio of 1%, and so actually I can search for these sterile neutrinos. Now, if I want to compute more precisely their number density, I have actually to solve the Boltzmann equation. Again, long formulas, so I will have it here. So first of all, you need to look at the mixing angle. The mixing angle is not just the mixing angle in vacuum, but you are in a thermal bath, and there might even be a lepton asymmetry, which would induce matter effects like the matter effects we have discussed yesterday in presence of a background which is CP violating or CPT violating. So if you have a lepton asymmetry, so a difference in density between neutrinos and antineutrinos, that will induce the matter effects I discussed yesterday. So in fact, the mixing angle I have to look at will have here these matter effects in presence of the lepton asymmetry and these thermal effects, which also suppress oscillation, because again, thermal effects come from the interactions with the background, and these interactions are due to charge current and neutral current interactions, so they select the flavor, so they will tend to suppress oscillations. So if I want to compute this properly, I need to solve the Boltzmann equation, which is given here. This is the distribution of these nearly sterile neutrinos, which will be given by, this is the interaction rate of the active neutrinos, because I need those, well, I cannot get there, but I need those interactions to happen. So when you get to 1 MeV, you don't have any more active neutrino interactions, so you cannot produce these particles anymore. This will be controlled by the mixing angle in matter that you have here, which controls the probability of oscillation. And then usually this is the density of active neutrinos. You can neglect this term at least for kind of KV sterile neutrinos. And this is the Fermi-Dirac distribution that I already talked about earlier. So if I solve this, actually, for those of you who are interested in neutrinos cosmology, this is a nice exercise to do. It's possible to solve this analytically, and you get a contribution to the energy density of the universe, in particular to omega, which is in the right ballpark if I have very small mixing angles in vacuum and masses in the KeV region. So that's why for a long time these these sterile neutrinos have been particularly interesting, because you would get a warm dark matter candidate with a very simple production mechanism. What has happened in recent years is that on one side you have constraints, we can see it from here, from structure formation, in particular Lyman alpha. So if these neutrinos are too warm, then they will exhibit some of the features that I already discussed. They will tend to erase the structures at smaller scales. And again, by measuring the power spectrum, I can constrain the masses. So these type of cosmological observations push the bound on the masses to higher and higher values, more towards the several keV, not 10 keV region. At the same time, so you have the decay, as I already mentioned, with a branching ratio of roughly 1%, you have this decay. So you can have the neutrino going, the nu4 going into neutrino gamma. This is at rest, is a two-body decay. So the energy of the photon is the mass of the neutrino divided by 2. So what you can do is search where you have high concentrations of dark matter, like centers of galaxies, dwarf galaxies, that you can go and look for X-rays, because these have energy in the KV region. So X-rays, but over the background of X-rays, you expect a line to appear. And this is the way to search for these sterile neutrinos. Now, it's interesting that indeed, so this is the latest compilation of bounds that I could find. So these kind of lines here correspond to the constraints from X-ray searches. And this is where the mechanism of production I discussed, this is called the Dodelson-Withrow mechanism. So somehow you see you need some other mechanisms. There are, for instance, I can switch on a lepton asymmetry. If that is present in the early universe, what it will do, it will change, maybe I have a plot here, yeah, actually. It will change the profile, kind of the distribution, the momentum distribution of these sterile neutrinos. In particular, you see, it will tend to shift it to low momentum, making it colder and so making it more compatible with structure formation. There are even other ways, thinking of producing these sterile neutrinos from decays of heavier particles much earlier on in the universe. That makes it even colder. And so using a different type of production mechanism, you end up having the right amount of asymmetry compatible, of density compatible with these X-ray searches. I want to mention, because this is potentially interesting, that a couple of years ago, indeed, they found this line. I mean, this line is what you see here. I mean, it's not exactly a line. There's a little bump in the distribution by two groups independently. And if this is confirmed, this would indicate a sterile neutrino with a mass of, well, actually 7 keV, not 3.5, is the double of the energy that you observe. So 7 keV sterile neutrino with quite a tiny mixing angle. And then you have to think what is the production mechanism, because Dodelson-Withrow doesn't work for these values of the mixing angle. But you can think of, as already mentioned, a lepton asymmetry or some decay mechanism. It is a bit controversial. Here you see different X-ray searches kind of pose different constraints. Some seem to favor this interpretation, some seem to disfavor it. So the situation is still a bit controversial, but is indeed interesting, so I decided to mention it. And finally, we move on to leptogenesis. This happens at much earlier times, and it directly links with the seesaw model, so other models of neutrino mass generation. And what is nice is that some is a natural byproduct of this mechanism of generation of neutrino masses, and can explain one of the key questions that we have in in cosmology, which is the origin of the baryon asymmetry. So let's go back. Well, let's first look at what are the key elements, and let's go back to the seesaw mechanism we discussed earlier on. So in order to generate a baryon asymmetry starting from zero baryon asymmetry dynamically in the early universe, you need to satisfy the so-called Sakharov conditions. So what are these Sakharov conditions? But you need, first of all, to violate the baryon or lepton number. You need baryon violation, but lepton number violation works as well because in the standard model, remember that in the standard model, B minus L is conserved, but B plus L is not at the non-perturbative level, right? You must have seen this in the standard model lectures. So if I'm able to generate a lepton asymmetry, then Sphaleron effects, which are these non-perturbative effects which take place, will convert this lepton asymmetry partially into a baryon asymmetry. So either of these two conditions is sufficient, well, not sufficient, is necessary to generate a baryon asymmetry. Then you want C and CP violation, because otherwise you will have a process which generates a baryon asymmetry, but then you will have also the conjugate process which will erase the baryon asymmetry you have produced. And then you need out of equilibrium. Again, this is due because if you have a process which produces a baryon asymmetry in equilibrium with the same rate, you will have the inverse process, which will then erase the amount of baryon asymmetry you have produced. So if you satisfy these three conditions, then you can see if your model can generate a sufficient baryon asymmetry. So let's look at that in seesaw models. Let's recap what we said this morning. So in a seesaw, and let me do that in seesaw type 1, which is the simplest case I can consider here. So we introduce a right-handed neutrino, which carries lepton number, and then this will couple via a Yukawa coupling to the Higgs and the left-handed doublet, and we'll have a certain Majorana mass term, which in many models is taken to be very, very heavy, because there's no good reason why it should be light. So one thinks of bringing it to the GAT scale. So let's look at this from the point of view of the early universe. So at temperatures which are above the mass of the right-handed neutrino, all these interactions, these Yukawa coupling, Yukawa interactions, and any other interaction the NR can have, will keep it in thermal equilibrium. So, what happens as the temperature drops below? When the temperature drops below the mass of the particle, then let's think of, I have this interaction here. So in equilibrium, this can go both ways, because these particles have sufficient energy to produce back a right-handed neutrino. We are in a thermal bath, and so this can go either way. But when the mass, when the temperature drops below the mass of R, it means that the energy of these particles is lower than the mass of the right-handed neutrino. So the only thing which can happen is the decay of the right-handed neutrino, but there cannot be inverse decay. It cannot be produced back. And so what will happen is that NR actually decouples, but most importantly, from the point of view of leptogenesis, the only thing which can do is that NR will decay. And if the decay rate of NR, which goes into neutrino or lepton, charged lepton, is different from the one of the conjugated channel, you will end up producing an excess of leptons, so a lepton asymmetry, which then one can convert into a baryon asymmetry. So this is the basic picture. One has to remember that the decoupling is not instantaneous, so it will take some time after the temperature goes below the mass of the right-handed neutrino for these processes to shut off, and any other lepton number violating processes which involve the right-handed neutrinos. So what will happen is that not all the lepton asymmetry you are producing in principle remains in the early universe, because these inverse processes a little bit will erase it. And so these are called washout effects, which depend on the model you are considering. And typically can reduce the original, the kind of the baryon, the lepton asymmetry that you can potentially have by a factor of from several to a factor of 10 to the minus 2, 10 to the minus 3. And then Sphaleron effects will convert this lepton asymmetry into a baryon asymmetry. And which is what we observe today. So if I put all of it together, I get that the baryon asymmetry that I observe, this is the number density of baryons minus antibaryons divided by the entropy, is given by a factor K, which is the washout effect. G star comes in because you dilute by entropy from when you produce the baryon asymmetry to now, and then you have a factor which takes into account the Sphaleron conversion of the lepton asymmetry into a baryon asymmetry, and this is the CP asymmetry, which is the difference, the weighted difference of those two decay rates. So, and which is typically, roughly, as I said, 10 to the minus 3 to 10 to the minus 4, the decay asymmetry. Where kind of the neutrino physics enters is here. So the parameters, for instance, of the CISO model, etc. So if you're trying kind of to, I cannot say test, but get information about the viability of leptogenesis in the specific model you are considering, you will be interested into the CP asymmetry. How does the CISO mechanism satisfy all the Sakharov conditions? Well, you have lepton number violation in the neutrino, Majorana neutrino mass for the right-handed neutrinos. You will have CP violation if the Yukawa couplings have imaginary phases. And out of equilibrium is automatically satisfied because of the expansion of the universe, so when the temperature drops below the mass of the right-handed neutrino. So you satisfy all the conditions, and indeed, leptogenesis in recent years has emerged as one kind of the favored mechanisms for explaining the baryon asymmetry, because it is not only you can explain the generation of a baryon asymmetry, but in many models, you can also explain a value which is big enough to be compatible with observations. And this is actually quite tricky. I mean, in electroweak baryogenesis, you also discussed. I mean, you generate a baryon asymmetry, but it's not sufficient to explain what you observe. While here, in many models, you can indeed get to the values we have observed observationally. So maybe I just want to mention one thing, which is, can we test it? But first of all, we cannot test it for sure because this happens at least in CISO type 1 at scales we cannot access directly. So what you would have to observe the NR, test, measure the couplings, and then you would see if you get the right amount of baryon asymmetry or not. We cannot do that. But what we can do, we can actually check if the conditions which are necessary for leptogenesis are satisfied. So we can search for lepton number violation in neutrino double beta decay and CP violation. As I said, the easiest way to do that is in long baseline neutrino oscillation experiments. We could also have the Majorana phases. Indeed, they play a role in leptogenesis. They enter in the epsilon parameter, but they are much more difficult to access experimentally. So, in my opinion, if we observe both lepton number violation and CP violation, then this would be a hint in favor of leptogenesis, although, of course, not a probe. We can do something even more. We can try to see if in a specific model which explains neutrino masses and mixing, we can get the right amount of the baryon asymmetry, because we're not ultimately interested in having a generic neutrino mass model. We want a mass model which explains what we observe in terms of masses, mixing angles, CP violating phases, so with flavor symmetries or some other mechanism. And there, the number of parameters which are involved is going to be much smaller than the generic model. And so it's possible to constrain, maybe even measure some of these parameters directly, and then at that point you can predict the value of epsilon and you can check if the baryon asymmetry you get is the right one or not. Obviously, this is a model-dependent statement. It will be in the model that you have chosen to explain neutrino masses and mixing. In fact, there is quite a few works which look at, for example, leptogenesis in flavor symmetries to explain the flavor structure. I think there's some more considerations in the slides about some connections between low energy CP violation and the baryon asymmetry, but I think maybe we should stop and take and see if there are some questions. No, actually, before stop.